Okay, welcome everyone to this third webinar of the ENOS experience sharing focus groups. I think we are about on time, just 5 minutes late. We had some issues to fix, but I think that's okay. I hope you can see my screen, and I hope you're familiar with the webinar tool we are using. I'm not sure what you can see, but I guess you can see me and the panelist as a webcam, and maybe you can also see my PowerPoint. So I will speak a little bit about your what people can do to ask questions a bit later. Right now, I will try to make I will speak about a bit about this webinar. So it's part of the project ENOS, which is H2020 project, which means enabling onshore storage. And one work package of this project is deals with international cooperation and knowledge sharing. We have a few various tasks. We have some site twinning activities going on, some leakage simulation alliance for small leaking simulation sites, and so experience sharing focus groups, which is what we are doing today. So quickly, what are these experience sharing focus groups? It's meant to be so either webinars or workshops open to everyone, researchers all over the world, and they're based around specific issues, each on a predefined topics, and it's rather different than research priorities. The goal here is more to remove practical hurdles to running a successful pilot site. So if you're attending this webinar, you probably received the email from our mailing list, but if it's a colleague that transferred it to you and you want to join our mailing list, you can drop me an email and I'll make sure you will receive our next invitation. You can see the program we have for these experience sharing focus groups. So we already did 2 workshops and 2 webinars. The first webinar actually was on data archiving and management. The second one on smart drilling and reduction of costs. And you can find this on the website, and on, I think the recording is on YouTube as well. So today we have this webinar on CO2 supply, on-site handling and injection strategies. And you can see also the program that we have for the next, which is still open to debate. Actually, we still need to discuss and fine-tune this program. So today, the third webinar is about CO2 supply, on-site handling and injection strategies for CO2 storage pilots. The main idea was mainly for small pilots that are not integrated in a full chain CCS project, where there's a capture, transport, and storage all together. For this pilot, they need to find a CO2 source if they want to inject, and it can be an issue, a challenge. So we wanted to have a small event to discuss existing experience and provide practical recommendations and some interesting issues to be discussed. But we can have also others, are the pros and cons of possible sources of CO2 and possibilities for transport to the injection site, how to store CO2 on site before injection, recommendation for optimal injection parameters, etc. I think we have a very good program today. We have 4 presentations. So the first one will be by Puneet Sood, I hope I'm pronouncing correctly, from Air Liquide, and he will talk about Air Liquide leadership in CO2 supply chain in Europe and engineering solutions for CCS. Then we'll have Wallace and Vello from Advanced Resources International, and they will speak about CO2 supplies in the USA, more on the CO2 EOR experience. Then Sanjay Mawalkar from Battelle will speak about how they achieved 1 million metric ton CO2 stored, measurement and accounting for net CO2 injection in a CO2 EOR complex. And the fourth presentation will be from Juan Marin and Juan Carlos de Dios from CIUDEN, talking about CO2 handling and injection in a deep saline aquifer, experiences from Hontomin Technology Development Plant operation. And I will be, so I'm Thomas Leguina, I will be sharing this session. We will take questions during the whole webinar. I will try maybe to answer some questions at the end of each talk, and if the discussion becomes too long, we will postpone these questions to the end of the webinar. So let me just remind you that it's a webinar, not a web conference. So by default, all your microphones and webcams are muted, except for the organizers. There's a question panel in the software. So this is a preferred way to ask a question. Just write your question. If you really want to speak, then you can raise your hand. I hope I'm able to see it. Otherwise, you can ask a question and ask to speak, and I can give you and I can allow your mic to be open. And I think that's about it. I want to thank so the other ENOS partners that helped me in this webinar, which are Vitladik, Carlos de Dios, and Alberto Petinao, and also OGS and all the staff at OGS for the support, because they're providing the solution for this webinar. So I won't be longer. I think I will give the floor. So the first speaker is Puneet from Liquide, and I will give him the floor. Okay.
Okay, so is my screen visible?
It's okay.
Okay, so good evening, good afternoon, or good morning to all the participants around the world. I'll start with a small introduction about myself. I am Puneet Sood. I work for Air Liquide, and I represent one of the corporate functions. And I am Global Product Manager for carbon dioxide, which is one of the key molecules in our portfolio. In my role, I focus on developing new applications as well as technologies for production of CO2. Okay, so as customary, I would start with a small introduction about the companies for those who do not know about Air Liquide. We are world's leader in gases, technologies, and service for industry and health. We are present in almost 80 countries. The group revenues were totaling about 20.3 billion euro in 2017. And Air Liquide's culture is strongly driven by innovation and customer centricity. So in 2017, if you see there, we spent about 292 million euros in innovative projects, and we filed about 318 patents with 3,800 employees out of a group of 65,000 employees globally. There are 3,800 employees who are working every day on developing new innovative solutions for our customers. Okay. Now, I think in continuation to the innovation efforts, let us not forget that CO2 is an important molecule which is essential for presence of life on the earth. But at the same time, CO2 is also important because it contributes to global warming. And Air Liquide, a signatory of United Nations Global Compact, released its climate change objective in November 2018, where we declared to reduce our carbon intensity by 30% between 2015 and 2025. So what does this mean, basically? So we call this program internally as ACE. In ACE, A stands for assets. And as a company, we can focus on our assets by improving efficiencies, lowering energy consumption, and by choosing the right technology. Last but not the least, also have the right energy mix. That is, have more renewable energy in our sourcing, because we are quite energy intensive industry, and finally gaining efficiencies through distribution and supply chain. The C here is for customers, and we strongly believe that the customers are the most important pillar in the journey. And here we want to reduce the carbon footprint by providing innovative technologies to our customers, like oxy-combustion, for this particular CCS application, providing equipments and innovative solutions for that. On-site production of gases, which eliminates emissions from transportation, supplying to our customers through pipeline, and developing new solutions for sequestration and have a circular economy. So the last one is E, which is the ecosystem, and this is where I spend most of my time in developing an ecosystem of startups or innovative technologies to build a pipeline of opportunities which one day would become a reality. Our current operations and future initiatives are assessed by rating agencies, which are listed here on the left side of my screen. And you will see that all these reputed rating agencies evaluate on number of parameters to give us these scores. And among other efforts related to our commitment towards climate change objective, we are also trying to decarbonize our hydrogen and bringing the extracted CO2 from SMR operations to our customers. One of such examples is in Port Jérôme in France, where we use our patented cryocap technology to produce 300 tons of CO2 per day. And this is a byproduct which comes from SMR or a hydrogen plant. And this way we try to decarbonize from our own production. I thought it's very important to touch a little bit on this topic before I start getting into some of the other solutions, because I personally feel and believe that due to change in regulations and policies, in less than 10 years from now, it will be an important topic of interest in a forum like this. Therefore, to stay ahead of laws and regulation and policy makers, and to contribute positively in reducing carbon footprint from our operations, we spend approximately about 100 million euro per year to reduce the carbon emissions from our, I don't know how these slides got up and down. Okay, so if you see that there are a number of emitters of CO2, and there are some high concentration of CO2 sources coming from byproducts, and there are some lower concentration. The high concentration CO2 emitters are the ones who are producing fertilizers, bioethane, ethanol, or even CO2 wells. While the CO2 concentration is more in range of 98 to 99%. And then we have other sources like hydrogen SMRs, which have a concentration up to about 40%. The last ones would be the flue gases coming from pulp and paper, coal power plant, IGCC power plant, steel production, and so on. So basically, there are three kinds of sources. And if you see on the right in the pie chart here, the rich sources of CO2 are the ones which are preferred by the industry to extract CO2 from as a byproduct from these operations. And you see largely that most of the CO2 is extracted from the fertilizer industry. The ammonia is one of the main suppliers or emitters of rich CO2 in a concentration of about 98.5%, followed by petrochemical operations and then bioethanol. So basically, if you see, out of the 20,000 tons per day which is produced in Europe overall by 100 plants, the 48% of the product is coming from ammonia. And if we go back to the summers of 2018, I'm sure many of you will remember that there was a CO2 crisis right in the peak of summer and during the FIFA World Cup. And this was basically not because there was no CO2 available, it was because of the primary production of ammonia was affected because of higher natural gas prices, and the industrial gas companies struggled to get CO2 to their customers who produce beer or other carbonated drinks. So that's more on the supply side. I would talk a little bit here about Air Liquide now. Since you have understood the supply side, I would say that it would be good to have understanding how Air Liquide is organized around the CO2 business. We operate 30 plants, and 60% of these plants are independent of the fertilizer sources. So, which means it's quite diversified, and we have a strong reliability in our supply chain. I'm sure with the situation I explained in the previous slide, how important it is to see that diversified sources is important to have a reliable supply chain. We have a total production of 1.6 million tons per year, out of which we supply about million tons to all our customers by driving. So there's a difference of about 600,000 tons in a year. The production is 1.6 million, while we deliver about 1 million tons to our customers. So this is coming because of the seasonality effect. During the peak summers, we would run our plants at 100%, while in winters, this consumption may go down to about 50%, or which is a lean period for us. Read through them. We have about 250 trucks and 50 wagons, wagons which cover about 20 million miles, million kilometers in a year to deliver more than 3,500 customers all across Europe. So in the last 10 years, we continued our strategy to diversify our supply chain. In the last 10 years, we invested in about 13 plants, out of which 10 were biogas and bioethanol and biomethane plants. 2 were hydrogen SMRs, and 1 was a nitrogen fertilizer. 1 was coming through a fertilizer source. I think as customers, you would like to know how the supply chain works. In the CO2 business, I would say the quality is the most important, as CO2 either gets mixed into our final product, example, the cola drinks, beer, or carbonated other beverages, and it also gets in touch with our food during chilling, freezing, or transportation operations. Hence, we apply very stringent processes to control the CO2 quality throughout the supply chain, from the time we purify, liquefy, store, and transport to our end customers. The process starts with capturing of CO2 as a byproduct from the operations of fertilizers, petrochemicals, bioethanol plants, etc., which I have explained earlier. And removing volatile organic impurities and particles are more important to make sure that we have stringent quality process throughout the supply chain. So after that, we move this liquid product either directly to our customers or to our filling centers, where the liquid product is filled in smaller capacity cylinders, microbulk, or sent to the dry ice plant for converting the liquid CO2 into dry ice. As customers, I think it is very important for all of you to understand how the cost structure works, or how the cost is built up. So if you see on the top, Air Liquide invests millions of euros in state-of-art primary production facilities along with sophisticated analytical equipments. It also invests heavily in supply chain of assets. Remember the 250 trucks with trailers and 50 wagons, rail wagons, which are used to supply our customers, and it is a strong backbone of our supply chain, as all these assets mostly belong to Air Liquide. Finally, we also invest in storage tank and distribution equipments on our customer side, so that the customer just sees the molecule and he needs to be focused more on the application and not getting concerned on how the product CO2 is produced and getting delivered to them. In return, what we charge is monthly fixed fee, which covers all the investment which is shown on the top side of the slide, and a variable fee which is required to transport the molecule and produce the molecule, all the operational cost. I would also like to highlight here, since CCU is a kind of application which can be planned, if the requirements for CCU applications come during the winter months or the lean period where there is excess of CO2 produced, that is the time when it would be easier to manage the gap which we have between supply and demand during the peak period and the lean period. So this brings me to the last slide, and I'll talk here about our past experience and give a brief about process description which we had on Profendra project in Iberia. So this installation was designed and commissioned to supply CO2 in different states, gaseous, liquid, and supercritical, to different supply conditions in terms of flow, pressure, and temperature to meet the needs of carbon capture and storage project. The installation consisted of bulk carbon dioxide storage tanks. There were cryogenic pumps located next to the tank to increase the pressure to the desired value. These pumps were used to regulate the flow and pressure of carbon dioxide in various phases, gas, liquid, and supercritical. There was also a gasifier next to the tank, which used natural gas boilers to heat the water that was used as a hot fluid in the heat exchanger. The gasifier was used to control the outlet temperature of CO2. The supply line for the outlet of the gasifier, or at the outlet of the gasifier, was provided to deliver the carbon dioxide in the gaseous as well as supercritical phase to reach the injection wells. The installation was also integrated with the electrical control panel, through which the input and output of the signals could be modulated, could be managed, and to modulate the CO2 flow. The control panel could be operated remotely, which was one of a good feature. And finally, the pipeline was designed to install traces to detect CO2 flow and connected bottles to other gases for detection of various parameters which were required to moderate the flow, pressure, and temperature remotely. So with this, I come to the end of my presentation.
Okay, thank you, Puneet. I see I have one question from the attendees. If you have other questions, it's a good time to ask. So the question from Vitladik is, do you also use any natural geological CO2 sources?
In the sourcing mix, there is a dependence to natural sources, which is the CO2 which comes from the well, and in the industrial language we call it CO2 coming out from below the earth. Yes, it is there, and if we go back to the presentation and see the sourcing mix, there is about 12% of CO2 which is coming from natural wells. This is for CO2 all across the Europe throughout the industry.
Okay. Okay, I see. I just wonder. So you say I want to go back to your slide on the cost structure when you mentioned that. Just to be clear, you mentioned that the key for supply to CCS projects could be leveraging on seasonality impacts. So that means that you're kind of recommending that it's better to inject in winter, as I understand.
I mean, this was one of the suggestions which I wanted to make is during peak summers, there are applications where the industry always requires or the capacities are always providing the molecule to the customers which need the most. And CCS activities, if they can be planned in advance, there could be excess molecule which could be available to inject into the CCS plants or the projects. So if you remember, like with Air Liquide itself, we have a production capacity of 1.6 million tons per year, out of which 1 million ton is what is delivered. So this impact of, or the difference of 600,000 tons is basically due to the seasonality impact. And this molecule could be available if the activities are planned a little bit in advance.
Okay, so we have two more questions from the attendees. The first one from Thomas Berly is, what is the price of highly pure CO2, say for food and beverage, in dollar per ton?
I think it's quite relative, and the price throughout the Europe would depend on number of factors. It is basically a microeconomics case most of the times. If you have more supply than the demand, the prices are low, and if there is more demand than supply, the prices tend to go up. And it's not hard and fast rule that we can say there is a price. There are other elements which are also contributing to the cost, would be the distribution cost. The further away you are from the production plant, the cost is going to increase.
Sure, thank you. And the other question from Timur de la Haye is, does Air Liquide supply biogenic CO2?
Yes, if you see in the set of plants which I showed you and the recent investments which we have made, what can be considered first of all as biogenic CO2 or bio CO2? So any CO2 which is coming out of non-chemical activity, for example, biomethane or bioethanol, where you use energy crops or corn as a feedstock. Those are all, they all can be considered as a short carbon cycle where you produce CO2 from anaerobic digestion, basically, from the agricultural waste most of the times, yeah.
Okay, I have a last question before we change, we go to the next speaker. How do you trace the CO2 source to identify the source that may be out of spec?
Sorry, can you repeat again?
So how do you trace the CO2 source to identify the source that may be out of spec? So I guess it's...
Okay, so when we do, so this goes back to a little bit upstream, we go back to a raw gas source, and before putting the purification, liquefaction process, in place or during the capturing or before even capturing the CO2, we would analyze the source for the kind of contaminations it would have and make sure that the process upstream of the byproduct is in place, because this is something which is very important. We need to understand what would be the kind of contaminations which would come with the raw gas and what would be the kind of contamination which could pass through in the end product. And as I said, it is important as the final product and CO2 which gets in close contact with the food which we eat and also get dissolved in the product which we drink. So it's important to make sure that at the first stage when we select the raw gas source, it follows the required parameters to bring up the final product to a food and beverage grade. I hope that answers the question.
I hope it answered the question. Anyway, I thank you. I think we need to go to the next speaker. So thank you again, Puneet. I will now mute you. So we give the floor to Matt Wallace, and just give me a second so I can give you the screen. So, okay. We can see the screen. Perfect.
Yes. Good. Shall we start?
You can, yeah.
All right.
You can start. Thank you.
Good morning. We're here, Matt Wallace and I, Vello Kuuskraa, are pleased to take part in this very interesting webinar. And we're going to talk mostly about CO2 supplies, how they're linked with enhanced oil recovery, and other features that have enabled the capture and storage of CO2 to take place in the U.S. I'm president of Advanced Resources International. Matt is a senior consultant with our company. And we're providing this presentation with support from the U.S. Department of Energy, National Energy Technology Laboratory, where we're helping them conduct a number of projects in the U.S. Just a few words about Advanced Resources International. We have over 40 years of experience with CO2 enhanced oil recovery, both in the US and overseas. And for the past dozen or more years, we have brought this experience to storing CO2 in saline aquifers as well as in oil fields. We have also operated and have operated a variety of field projects at Plant Daniel, a coal-fired power plant where the CO2 was trucked in. Also at the Citronelle Dome, that involved a 15-mile CO2 pipeline from a CO2 capture pilot plant at Plant Berry to the field site. And then most recently in Kemper County, we're involved with Southern Company and Mississippi Power in the U.S. Department of Energy in basically designing a large regional storage capacity. So let me then jump ahead to the next slide. I'm going to talk a little bit about a background on EOR, enhanced oil recovery, and some history, how it started. Then I'm going to turn it over really to Matt to talk about where the status is. Then I'll come back at the end with a look at Weyburn, which really was the first to link CO2 EOR and CO2 capture and utilization, and then take a bit of a look into the future. Okay, just to a couple words that the use and storage of CO2 in oil fields, is relatively simple in concept, but it really requires sophisticated design, modeling, and monitoring. And an important point is that the CO2 that comes to the field ends up staying in the reservoir. The CO2 that gets produced is re-injected back into the reservoir, and at the end of the project, the wells are closed. And just some recent projects in the Gulf Coast, you find that CO2 enhanced oil recovery can provide about as equal with initial primary and secondary recovery. And that should be reasonably consistent with its application elsewhere. Okay. Just a brief history. It all started back in 1972 when CO2 was captured from natural gas processing plants in the southern part of West Texas, and then piped about 200 miles to the Sac Rock oil field. With that experience and the discovery of larger natural sources of CO2, major pipeline systems, and Matt will talk a little bit about those, began to bring CO2 to the large oil fields in the Permian Basin. And then a third, I think, very important step in this linkage was the cooperation between US and Canada on capturing the CO2 from the Dakota gasification plant in North Dakota, transporting it 200 miles across the border to Canada, and using it and storing the CO2 in the Weyburn oil field. And I'll chat a little about that as well. And then more recently is the expansion of both CO2 EOR. It's capture from a variety of sources, natural as well as industrial, both along the Gulf Coast and in the Rockies. Okay.
I will just provide words here to bring everyone up to speed on where the industry stands today. First, a little bit about the CO2 EOR oil production side. We've really come a long way in the last 30 years or so from roughly 50,000 barrels a day in the late 80s to, as of 2014, around 300,000 barrels a day. As you can tell from the graph, roughly 2/3 of that oil production is coming from the Permian Basin still. But we've had significant developments in the Gulf Coast and the Rocky Mountains, as well as the Mid-Continent region in Oklahoma, contributing some significant oil production to that total. Today, in the last 4 years or so, we're at roughly 320,000 barrels a day. We've added a little bit to that total. Despite some oil price fluctuations, the industry's remained relatively steady and actually increased the total oil supply. And that's from roughly 135, 140 total projects in the US. Most significantly, though, I think it's important to note that CO2 EOR is really CO2 limited. There's a limited supply, and as soon as that supply increases, total EOR will increase along with it. We'll take a look at a few of the major regions now. As we mentioned, the Permian Basin of West Texas is really the heart of CO2 EOR in the US. This is an overview of the CO2 pipeline system. You can see in the southern portion of the map, the Val Verde gas plants. They were the original sources of CO2 for EOR. They're still in use today, although diminished capacity somewhat. Near their location, you see the Century gas plant, which is providing a significant amount of CO2 for EOR today. And then in the northern regions are the natural sources, McElmo Dome, Doe Canyon, and Bravo Dome. They're providing about 30 million tons per year of CO2 for EOR. And they arrive in the middle of the Permian Basin at Denver City through the major CO2 pipelines. The blue lines are the regional distribution systems that take that CO2 from the sources and deliver those to the fields. Overall, we have about 1,500 miles of pipe. for large scale, and then about 700 miles of the distribution lines. This is the current infrastructure map as it stands today, including the Gulf Coast of Louisiana and Mississippi, where Jackson Dome is our natural supply that supplies the Gulf Coast, and Wyoming, which is provided by industrial sources of CO2 to EOR. And then in North Dakota, we have the Great Plains Synfuel plant, which Vello will talk about in more detail, delivering CO2 to the Weyburn field. And I believe another talk in this presentation in Michigan from the Antrim gas plant, delivering CO2 to the fields for core energy. All told, there are about 3,500 miles of CO2 transportation pipelines in the industry. So I'll just touch briefly on the other regions, the Gulf Coast and the Rocky Mountains. The Gulf Coast primarily uses natural CO2 from Jackson Dome, delivers that over 750 miles of CO2 pipeline. We also bring in modest amounts from industrial sources, including PCS nitrogen plant and air products plant. A new field at Petronova, we'll discuss that later on in the presentation as well. And as well as the Rocky Mountain region, which is primarily located in Wyoming. Industrial CO2 from the large Chute Creek gas plant, as well as the Lost Cabin plant, delivers CO2 to multiple EOR projects in Wyoming. There's also some planned CO2 delivery pipeline to fields in Montana and North Dakota that should be built, within the next few years or so, depending on a few things. So now Vello will discuss a little more about Weyburn.
This is, I call it, the first poster child of carbon utilization, or CCUS. And it really demonstrated that you can have a full value chain working here. You have the CO2 source at Beulah, North Dakota. There's a 200-mile pipeline that crosses the border into Saskatchewan. And then the CO2, it's used for enhanced oil recovery, but also it's the world's largest CO2 storage project at this point. We had the pleasure of working on this project for about 3 years to really help optimize it with the operator. And one of the important things was that both the province of Saskatchewan and the government of Canada provided certain incentives that encourages the additional storage of CO2 in the reservoir. And you can see that about 30 million tons will be stored with enhanced oil recovery, and another 10 million tons after that with in basically for storage itself. Okay. Okay. And now just a bit of a look into the future. Where will we get the CO2 supplies and pipelines? And I think you would have noticed that throughout this presentation, we've talked about the importance of pipeline and the fact that you can build large 500+ mile pipelines. I guess if you look at the extended pipeline system in the Rockies, you're talking about 700 or 800 miles. And I think that will be a critical piece of the puzzle for linking these many sources to various storage sites as well as oil fields itself. Some of the past studies that have been looked at this topic have been quite, I would say, conservative, pessimistic about the ability of pipelines to connect sources to sinks. And we'll come back to that a little more. Today, about 40 million metric tons comes from natural sources used for enhanced oil recovery. However, these supplies are limited, and the future will depend on increasing volumes of CO2 coming from anthropogenic or industrial sources. And there's a nice, several first steps have already been taken. We capture CO2 from natural gas processing plants, ethanol, nitrogen, fertilizer, hydrogen plants, and they provide about 20 million metric tons a year. The most recent one, and Matt mentioned this, is Petronova, and this is a post-combustion CO2 capture project with a pipeline that takes it to an oil field. And most exciting is that the U.S. government has passed Section 45 tax credits that incentivize capture and utilization of CO2 from power plants and industrial facilities, and they have to be linked to secure storage of CO2, which can take place in either oil fields or in saline aquifers. And this is Petronova. It's, as I mentioned, the most recent project, and I guess is the U.S. poster child. It is a post-combustion capture plant on a coal-fired facility. They capture 80 million MCF of CO2 per day, and is transported to an oil field about 80 miles away for use for enhanced oil recovery. And again, we've had the privilege of being able to work on this project. Next. And finally, as part of a larger study supported by a foundation as well as a carbon utilization research group, we looked at how might the linkage of CO2 sources and their storage areas, both for primarily here for enhanced oil recovery, play out in the future. And we designed a series of pipelines that would connect sources from the Gulf Coast, Texas, the mid-continent, with oil fields for storage, CO2, as well as enhanced oil recovery. And you can see 3 large long-distance CO2 pipelines, some as short as 200 miles, others as long as 1,000 miles. And then a variety of smaller scale gathering systems that would link basically sources of CO2 to oil fields. And scale is a very important part of it. It enables the transportation system to be quite cost effective. So with that, thank you for the opportunity to take part in this webinar, and we're open for questions.
Thank you very much, Vello and Matt. So do we have questions? Yes, we have a first question from Vit. Do you expect that the new 45Q tax credits will really cause new CO2 capture facilities being built?
Do we think that the new 45Q tax credit will
Provide new
facilities? Yeah. Oh, I think so. We're seeing considerable interest by industrial firms and even power plants who are looking at basically integrating storage, transportation, as well as the capture itself. There are a number of barriers. We still need the final regulations to come out. But we're seeing kind of the forward-looking companies already beginning to do some planning.
Okay. I have a second question from Edward Romanenko. Is there an estimate of CO2 EOR activity in the US as of 2018 or 17?
Yeah, well, there are no numbers that are published at the moment. We've done some work to bring those numbers forward from 2014. Roughly 320,000 barrels per day of oil are produced. Total number of projects around 140 of varying size, and I believe we're using CO2 roughly 3.5 billion cubic feet per day. It's about the same as it was in 2014. Some of the natural supply has fallen off, but we're adding new industrial sources. So hopefully we have some published numbers in a study, not too far in the future.
Okay, I think it's one of the common points with Europe is that it's more the supply of CO2 that is the limiting factor than any clients or sources of sinks of CO2.
Exactly. Yeah, supply is critical, and I think with 45Q adding some incentive that it's really a catalyst for the industry to increase supply and oil production.
Just as backdrop, if you store the CO2 in an oil field, you gain a credit of $35 per metric ton. If you store it in a saline aquifer, you would get a tax credit of $50 per metric ton. And that's designed to kind of equalize the two options. Surprisingly, it has created considerable interest in looking at saline aquifers and storage sites that are close to power plants.
Okay, it's really interesting. I have another question. Please, can you comment the numbers for storage? 2.4 million ton, 30 million ton with EOR, and 40 million ton with EOR/SEC. Do you differ sequestration and storage?
Well,
can you see the writing of the question?
About overall, we use about 60 million metric tons a year of CO2 and store it in fields. About 2/3 of that, 40 million metric tons per year, comes from natural sources, and 20 million metric tons per year comes from industrial sources, a variety of sources we talked about: gas processing plants, hydrogen plants, fertilizer plants, ammonia plants, and so on.
Okay, and do you know do you have all the CO2 that I expect some CO2 from the fields are reproduced? Is it recycled or what?
Yes, all of the CO2. CO2 is a valuable commodity. And with in an oil field and in a saline aquifer you don't recycle from a saline aquifer, but you get paid for storing and keeping it as much in the ground as you can. But all of the CO2 that is produced with the oil is recycled and put back into the reservoir.
Okay. I get the last question before we move on to the next speaker. Are there any active buffer storages in operation? How are the fluctuations compensated?
Are there some active storage projects underway, and how are they compensated? If you're using CO2 for enhanced oil recovery, you sell the CO2 to the oil field, and that's the primary compensation. There are, some projects that have been done on a pilot basis, like at Plant Berry, which transported the CO2 to the citronelle dome for storage in the saline aquifer. And that was supported by the Department of Energy, as well as Southern Company providing cost share to the project. So this was more of a small scale research project. But the large scale projects today have needed support from enhanced oil recovery for the sale of CO2. But with the 45Q tax credit, that will become the dominant source of support.
Yeah, okay, so the question maybe you heard me, you didn't get me. The question was more on the fluctuations of the supply of CO2, and is there any buffer storage at the site to compensate the fluctuation?
So if and the CO2 EOR operation begins, there's significant demand for CO2 at the beginning. You know, all of your CO2 is injected, and you're using 100% of purchased CO2 for the first few years of the project until you get some recycled CO2 where your demand for purchased CO2 decreases somewhat. So I'm not sure of any projects that have a sequestration. Projects will use the reservoir as sequestration. They will take 100% of their contracted CO2 volumes indefinitely. So it's sort of, you're using the reservoir somewhat as sequestration if you need to work a part of the field over or you know, continue development. But yeah, but oil fields will take all of the CO2 that they are contracted to take.
Okay, thank you. So I thank you again. I think we can now move on to the next speaker, which is Sanjay Mawalkar, sorry, from Battelle. So now we can hear you. Just a second so we can see your screen. Yes.
Can you see my screen? Okay.
Yes, we can see it. The floor is yours.
I am Sanjay Mawalkar. I'm based in Columbus, Ohio, in the United States. I work for Battelle Memorial Institute. We are a research institute that's headquartered here in Columbus, Ohio. This is the talk that I gave to the GHGT conference in Melbourne, Australia. So it's a variant of the same talk, basically, that I gave at Melbourne, Australia in the October of 2018. It's a conference held every other year worldwide. My co-authors on this project include Andrew Birchwell, Neeraj Gupta, Matt Place, Mark Kelly, Mr. Wenicky. We're all Battelle staff based in Columbus, Ohio. But we also have Robert Manis, who is the president and the CEO of Core Energy, and Rick Pardini is the general manager out there, who does all the day-to-day operations. Vello and Matt Place gave a very good overview of how the CO2 EOR works. Ours is a variant of a similar process whereby the CO2 that is acquired from a natural gas processing facility, the Antrim shale gas, is sequestered into the ground for the purposes of producing oil. The idea here is to go basically from a primary to secondary to tertiary mechanism, and the CO2 EOR is typically considered to be a tertiary mechanism. However, in our project in the upper part of the Michigan in the United States, most of the reefs where we are doing CO2 EOR have not had a secondary process of production, meaning it has not undergone water flood or steam floods, and these typically these reefs have only undergone primary production that we'll see in a little bit here. But the idea here is to inject CO2 into the ground where it mixes with oil and allows the oil to flow to your production well. And any of the fluid that's captured back from the production well is processed at a processing facility where oil is extracted from the remaining gas stream, which is recycled back to the ground. So there is typically no venting going on in these facilities. any of the gas that's recaptured or recaptured at the processing facility is sent right back to the reefs. What you're looking at is basically our project in Michigan Basin, a CO2 ER complex that's showing a lot of pipes and processing equipment. The silver-looking vertical stacks that you see out here are basically the high-pressure separators that processes the production fluids coming back, and we'll be talking about that in a little bit here. But basically, this is a complex that's owned and operated by Core Energy, which is based in Otsego County in Michigan, United States. Core Energy began its EOR operations in 2003. They also had conventional oil production assets that they're working with. Although the EOR that we're describing kind of was taken over by Core Energy in 2003, some of the reefs that are part of this complex have been doing CO2 EOR since 1996. So it's quite old at this point. The complex comprises of 10 reefs, Dover 36 production facility where the oil is separated from the recycled gas. And there's a bunch of network of gas and oil pipelines that transport CO2 to the reefs and then bring the production fluids back for processing. As I said earlier, the CO2 is sourced from a natural gas processing facility, which is called a Chesterton facility. It's basically an Antrim shale gas play, which is located about 10 miles south of this CO2 EOR complex owned by Core Energy. The CO2 is transported from that Antrim gas shale plant via a 6-inch carbon steel pipeline to the production facility first, and then from there it's distributed across various reefs that are operating currently. In this presentation, we're talking about basically a Midwest Regional Carbon Sequestration Program, which is a program funded by the Department of Energy, the NETL specifically. This has been going on for the last 6 or 7 years. It has gone through multiple phases. We are currently in phase 3 of the monitoring program that's funded by NETL. This particular presentation talks about the accounting methods and the CO2 EOR operations, whose primary objective was to safely store about 1 million tons of CO2 into the complex, which started basically in the February of 2013. That's when we started monitoring the operations of CO2 EOR that is run by the Core Energy. I'll be describing some technical details of how oil is processed and the recycled gas operations. Simple math, basically, that involves the mass balance of CO2. Accounting of net CO2 stored at a single reef, if you apply the mass balance formulas, we can somehow basically arrive at the net inventory of the CO2 that's left behind in a single reef. And the idea here is we're talking about the associated storage, or some of you might know it as incidental storage. CO2 is definitely an asset for Core Energy, so they would like to reutilize all of the CO2 that they can produce back from a reef. But it just so happens that over many years of operation, as you are carrying out your CO2 EOR, some of the CO2 is permanently lost into the reservoir. That's unrecoverable. So the accounting over the long term for a specific reef gives us an idea of how much CO2 is left behind permanently, or something that's uneconomical for us to produce back and send to other reefs. So similarly, if you do accounting at a single reef complex, we can go and apply the similar math to other reefs that are associated with the same processing facility and kind of get an idea of how much CO2 is left behind in the entire CO2 EOR complex. And we can take all of the numbers associated with this CO2 EOR complex and develop performance metrics from the accounting data that we have available. Now, Vello and Matt talked a little bit about primary production that range from 18 to 20% in the Texas Permian Basin. In the upper Michigan area where we're talking about the operations of these particular reefs, we have seen primary production recovery rates of approximately 34%. So there's still a significant amount of oil that's left behind. in the ground that could be recovered through other means. In this instance, CO2 EOR is directly used. Barring one or two reefs that have undergone some water or steam flood, bulk of these reefs have not seen secondary means of production. So they're basically going directly from primary production to your secondary means of production via CO2 EOR. Some of these reefs are new. So the Bagley Reef in this particular case and the Chester 16 reefs are actually new reefs, but the other 8 reefs are basically have been operating as active EOR reefs on a continuous basis since 1996. Some of them, of course, have been added recently. Typically, primary production, as I said earlier, is about 34%. So there's a fair amount of CO2 that still can be recovered back from these reefs. In this reef complex that started operating in 1996 until now, all of my data that I'm going to present here is through June of about 2018. We have new data, but we have not compiled it yet for presentation purposes. But the numbers are slightly off from that. Obviously, we have more CO2 sequestered in the ground. But the reef complex comprises of a total of 10 reefs, of which 8 reefs are active EOR reefs. And amongst those reefs, Dover 33 and Charlton 6 are considered to be late stage. So they've gone through a significant amount of CO2 EOR operation. And at this point, there's not a whole lot of economical oil to be produced back from these reefs. But these reefs are still attached to the complex because these reefs can be used for the purposes of storage operation. That means when you have excess CO2 available, you can put away safely any of the CO2 into the reef and then produce it back when you need it elsewhere where you may be doing a new CO2 flood. So as far as the new CO2 flood is considered, currently at this point in time, Bagley Reef, which started operating in 2015, and Chester 16 Reef, which started operating in 2017, are considered to be new reefs. Bagley is particularly a large reef that has undergone a lot of CO2 flood, and the Chester 16 is relatively a smaller reef that's currently undergoing CO2 EOR flood, a new flood. A typical flood may last a year or two at most, but you typically see most of these reefs have undergone a CO2 EOR flood, initial flood to pressurize the reef to bring it up to minimum miscibility pressure. That lasts about 12 to 18 month cycle. And once that reef has been pressurized, it undergoes CO2 EOR operations, where you may incur basically a continuous operation of CO2 injection and then production of fluids back from those reefs. This is the bird's eye view of the Dover 36 facility, which is the central production facility owned and operated by Core Energy. It's probably hard for some of you to see the details on this, but the silver stacks basically are the high pressure separators, while the green horizontal tanks that you see here are low pressure separators. Right here is a compression facility. These green tanks on the upper left of the diagram are basically the oil tank, which sends the oil to the marketplace. Back in the background here, you see an orange tank here, which is basically a disposal valve for the brine that is produced back from the reef. So brine is not sent back to the reef themselves. So as the brine is produced along with oil and gas, the brine is recovered and is actually permanently sequestered into a disposal valve at this facility. On the left of the diagram here, you see a bulk of the metering and the piping that's bringing all of the oil back from the reefs and the CO2 injection pipeline that goes out to the reef. All of the CO2 is basically transported via via pipelines. We don't have any trucks bringing in CO2 from the Antrim plant. Basically, the CO2 from the Antrim plant comes via a pipeline to this facility. It is commingled with all of the recycled gas and is sent back for a reinjection to a reef. This here is a very simplified process flow diagram of the CO2 EOR operations run by Core Energy. As I said earlier, there are 10, Chester 10 facility provides the pure CO2, which is basically the At the bottom right of your panel here, you're seeing the operation of the Chester 10 facility, which has 3 compressors currently that brings all of the CO2 to the Dover 36 facility here. The blue block here represents all of the high pressure separators that they have, and the lighter blue block down below here represents all of the low pressure separators that you have. In terms of the reefs, which are labeled here, Dover 33, for example, has a configuration of a single injection well called 133 and 3 production wells called 233, 533, and 933. Similarly, other reefs, for example, Bagley currently is not producing oil, and therefore you don't have dark black dots. So currently we're utilizing some of the wells for the purposes of monitoring pressure and temperature at the bottom of the reef. So it currently has 3 injection wells. Chester 16, which is another new reef, has a single injection well and 1 monitoring well. Some of the other reefs have different configuration. It is possible, for example, in case of the Dover 36 facility, is showing that it has 2 injection well and a single production well. So the production well produces a combination of oil, brine, and gas that's mixed in it. All of that brine, oil, gas mixture is brought back to the Dover 36 facility, where all of the production fluids are first sent to a high pressure separator. In order to preserve the pressure that's prevalent in the gas stream and reduce the compression costs, the operator would typically send all of the production fluids to a high pressure separator, where gravity is utilized to separate the liquid stream from the gas stream. So the gas stream that is produced back is recycled into a recycled compressor and is sent right back to the reef, while the liquid stream that comes out the high pressure separator is sent further for further separation to low pressure separators. So any remaining gas that is not captured in the high pressure separator is captured back into the low pressure separator, is compressed, and is sent back to the reef. The oil is sent to the market, and as I said earlier, the brine is sent to a brine injection well at site and is buried into the ground. The important point to note here is that on the injection side of things and on the production side of things, bulk of the metering is monitored via Coriolis flow meter. So consistently, the operator utilizes the same type of flow monitoring to keep the accounting accurate. So on the injection side of things, these are all the meters that are located and is measuring all of the flow rate of CO2 that is going to various reefs. In certain cases, we have flow meters installed at the reef themselves rather than at the Dover 36 facility. But in other cases, in bulk of the cases, the metering is done at the Dover 36 facility itself. Also on the production side, we consistently use Coriolis type flow meter to measure the amount of gas that is produced and is sent back to the reefs. Here we are looking at various pictures of the core energy facility. Currently, they have 3 compressors which are manufactured by Caterpillar. They capture about roughly 975 metric tons per day. I should mention all of my math or accounting is done on a metric ton basis, which is equivalent to 1 metric ton basically for us represents about 19,000 standard cubic feet per day. So 19,000 cubic feet of gas would translate roughly to 1 metric ton of CO2. Core Energy utilizes a TEG dehydration, which is the triethylene glycol dehydration system. So the CO2 that is delivered to Core Energy from the Antrim gas plant has some moisture in it that needs to be removed before it can be transported. So that CO2 is basically separated from the moisture using the triethylene glycol dehydration system. And that has a current capacity of about 30 mmCF per day, 30 million cubic feet of gas per day, which represents roughly about 1,000 metric tons of CO2 per day. Core Energy has exclusive rights to capture all of the CO2 that's coming out of the amine gas processing plant. Currently, the capacity is about 28 mmCFD, which is about 1,000 metric tons per day. Saltwater disposal is also present at this particular facility. So any of the moisture that is captured, and that it's about 100 barrels of moisture is captured from the gas stream that's coming in and that is disposed at the site itself. The inlet pressure coming into Core Energy's compressor is about 7 psi, and by the time it leaves the facility, it's between 1250 and 300 pounds per square inches, which is also the operating pressure of the compressors that's at the Dover 36 facility. So you can actually commingle the pure CO2 along with the recycled gas and sent back to the reef. Also, the configuration of the piping is such that you can allow a specific reef to obtain all of the CO2 on the pure CO2 that's coming from the Chester 10 facility, or it can have pure all of the recycled gas that's coming in, or it can have a combination of recycled gas along with pure CO2. So commingling is possible at this facility. Core Energy expanded or installed a brand new compressor back in March of 2017 that brought all of their purchased CO2 capacity to roughly about 1,000 metric tons per day. This is a simplified process flow diagram of the operation of the Dover 36 facility and the Chester 10 facility that goes through various cycles of compression and dehydration. All of the CO2 that comes out is basically almost pure CO2, and that about 99.7% pure CO2. And we have also seen that the recycled gas is almost about 96-97% pure, and we do not have much of hydrocarbon gas in this particular stream, and therefore any of the CO2 that is sent back to the reef for the purposes of CO2 injection is considered as if it's pure CO2. As I said earlier, the mass balance accounting method basically includes consistent basis of flow metering, which is measuring all of your accounting data via Coriolis flow meters. Coriolis flow meter gives you all of its mass on a mass basis rather than on volume basis. There are some vortex type meters that are attached to the low pressure separator, but there is not a whole bunch of gas in that particular separator. Those are measured on volume basis and are converted back to weight basis by using basically 19,000 cubic feet of gas equivalent to 1 metric ton. There is minor amount of venting. So basically when some of the compressors are forced maintenance or issues or things like that, there may be cases where the reef keep producing the gas and that gas is vented. But our accounting shows that the amount of gas that is vented is minute or is insignificant compared to the amount of recycled gas or is the amount of gas that is captured from the Chester 10 facility. Also at the Chester 10 facility, if there is any downtime where the compressors have to undergo maintenance, we would not acquire any CO2 from the Antrim shale gas plant. And the Antrim shale gas plant in turn would vent that gas, but it would not be vented by Core Energy at its facility. So typically these facilities are running on a continuous basis, and all of the monitoring takes place using computer system that captures all of the flow meter data on a minute by minute basis. So we get a large data stream that comes to us on a weekly basis, sometimes on a monthly basis, that we process at Battelle in Columbus, Ohio. And the basic math is really simple. If you want to understand how much net CO2 is stored in a particular reef, you just have to have a proper accounting of all of the injected mass of CO2 into that reef, and then subtract from that any CO2 that has been produced back from that particular reef. And over the long run, as I said earlier, if a reef has been undergoing CO2 EOR for 10, 15, 20 years, in certain cases even longer, for example, in the Dover 33 reef, that particular reef may have associated with it about 15% of the amount of CO2 kind of gets permanently left behind. So as an example, I'll be showing you a slide on Dover 33 as to what that number might look like. But typically on a long-term basis, between 10 and 15% of the CO2 appears to be permanently stored or left behind in the ground. So if you have an idea of a particular reef as to how much CO2 has been sequestered in that particular reef, you can actually go and take that map to your entire EOR complex, where in this instance, we have 10 reefs currently. So if we can do the math for one reef, there's no reason why we can add up all of the 10 reefs and arrive at the net CO2 that is stored across the entire reef. And our main objective over the last 5 or 6 years that we have been monitoring data is to safely monitor the storage of about 1 million metric ton. And we have actually already arrived at that particular number, as we'll see shortly. Some of the equation that is specifically recommended by EPA, which is the Environmental Protection Agency in the United States, it is basically an equation RR11, which is used for GHG reporting. It's a little bit more complex. I'm not going to get into the details of that, but I invite you to go to the EPA website and look up GHG reporting formulas. I said earlier that the recycled gas is almost pure CO2, and this is showing you the composition that we track. So basically, we have a meter, which is after all of the processing takes place, we have a flow meter at which the recycled gas can be sampled for the purposes of monitoring its composition. And over time that you can see is about 96% pure CO2. So when we recycle this gas back to the reef, we consider as if all of the CO2 is on a pure mass basis, and we do not distinguish it from the CO2 that's coming from the Chesterton facility. So we are now looking at basically a slide that shows us over the long term, or at least over the last 6 or 7 years that we've been monitoring since February 2013, the amount of CO2 initially for the first 4 years or so was approximately 15,000 metric tons per month, or on an average 500 metric tons a day. That capacity has now gone up, and a new compressor was installed in the March of 2017, and the capacity went up to roughly on an average about 27,000 metric tons per month, or approximately 1,000 metric tons per day. So over the last 6 years or so that we have been monitoring this particular operation at Core Energy, 1.1 million metric ton of CO2 has been delivered by the Chesterton facility. The next slide is the accounting methods for the Dover 33 reef. I don't know if you all can see, but the red line basically represents the amount of CO2 that is basically the net CO2 that is stored in the ground. The black thick line is the cumulative oil production, and the dotted black line represents the oil production line. So obviously it goes through a steep decline as CO2 EOR is conducted. The light blue dotted line is the amount is the recycled gas that is produced on a monthly basis, while the green dotted line represents the amount of CO2 that is injected on a monthly basis in this reef. And the difference between the amount of CO2 that is injected and the amount of that CO2 that is produced back gives us the red line, which is the cumulative amount of CO2 that is stored in this particular reef. A would represent the initial flood, in which in this case, Dover 33 had incurred about 120,000 metric ton of CO2 was required for initial flood over the first 10 months of operation back in 1996. And the EOR production began in 1997. Battelle actually conducted a storage test on this particular site. So the label C actually represents a time period when Core Energy turned over this reef to Battelle for the purposes of conducting a storage test. Battelle at that point had injected 270,000 metric ton of CO2 for the purposes of monitoring the bottom hole conditions, the temperature and the pressure. And then we had turned this reef back to Core Energy for CO2 EOR. So at this point in time, actually in June of 2018, we believe that Dover 33 has 335,000 metric ton of CO2 that's left behind on the ground, in the ground. So similarly, if we look at accounting for 4 other example reef, we're looking at on the top left is the Dover 35 reef, which currently has 223,000 metric ton of CO2. The second reef is Chester 2 reef, which has 262,000 metric ton of CO2. Bagley is a new reef that is still undergoing initial flood. This is a 3-lobe structure in which at this point in time 375,000 metric ton, and in fact as of about a week ago that number had gone up to almost about 500,000 ton of CO2. It's a large reef, so the initial flood at this point, and the operator is ready to do CO2 EOR in this particular reef. By the time they do CO2 EOR, it'll have 500,000 ton of CO2 in the ground before they resume a CO2 EOR. Similarly, Chartle 3031 is another reef that has net of 260,000 metric ton of CO2 left behind in the ground. So if we take all of the numbers around all of the 10 reefs that are associated with this particular complex, we have this next slide that shows us in the green bar all of the CO2 that's been injected so far. The black bar represents the amount of oil that has been produced. The blue bar represents the amount of CO2 that has been produced from that particular reef. And the orange color bars represent the amount of water. Some of the reefs have more water than other reefs. So for example, Charlton 3031 reef and the Chester Pie reef produces a significant amount of water that is produced and is sent to a disposal well. We have hardly any venting losses in this particular facility, and accounting, the long-term accounting that we have done shows that the processing loss, in the process of compression and transporting all of this gas back to the reef is insignificant. It's about 3.4% of the total amount of CO2 that has been delivered to this particular facility. So the net CO2 stored over the MRCSP phase 3 monitoring period is, we started monitoring this particular complex in 2013, and at that point, Core Energy already had about 1.1 million metric ton of CO2 in the ground. And then at the end of March of 2018, roughly, there was about 2.2 million ton of CO2 left behind in the ground. And therefore, the difference between the two, between February of 2013 and June of 2018, approximately 1.1 million metric ton of CO2 has been stored over the phase 3 of MRCSP monitoring period. Last but couple of slides talks about the performance metrics. So we take all of the accounting data and we have a bunch of performance metrics that we have developed around all of the numbers that are associated with the CO2 injection and the production. Things like the oil rate, cumulative volumes produced, incremental oil recovery factor, the voidage replacement ratio, recovery versus CO2 storage, the net utilization factor, the producing CO2 to oil ratio, maximum storage capacity. This is of particular interest to Battelle because we are interested in long-term storage or associated storage with the CO2 EOR operations. So we track this very carefully. And these reefs are considered to be like closed tank systems. So if you extract a pore volume of oil and brine and gas out of the system, that pore volume becomes available for future storage. So if you were to bring each of these reefs back to its discovery pressure, how much CO2 can be safely stored in these particular reefs is a metric that we actually carry out in this dashboard. So here is an example of an oil rate that is tracked during primary production of Dover 33 reef, which had a decline of about 18%, and then the CO2 EOR had a decline of roughly 20%, and in the second phase of the CO2 EOR, it was about 30%. So similarly, this slide is showing us that in Dover 33, you could leave behind without any problems about 360,000 metric ton all the way up to discovery pressure, which was roughly about 3,000 psi in this particular reef. The final key takeaways of CO2 accounting is that all of this data is really useful for GHG reporting purposes. Now, while the United States currently does not have a marketplace for trading in carbon, at least some of the companies, including Core Energy, are now beginning to report this data back to EPA. And those are called the MRV, or the Monitoring, Reporting, and Validation Plan, that have to be submitted formally to the government agencies. And the math around all of the accounting has to be reported on a consistent basis. year on. And then this data is also very useful for performing life cycle assessment of the upstream gate-to-gate CO2 operation and downstream emission to figure out if the oil that you're producing from these reefs or CO2 EOR operation is truly green. That means the CO2 that you are acquiring from your industrial sources, does that incur a penalty in its acquisition and its processing and its storage and transport that is not as green as we thought initially? But we have done analysis of our data, and it has shown that the oil that Core Energy is producing is quite green compared to other sources of oil. So that means Core Energy at this point is leaving behind significant quantity of CO2 in the ground, as opposed to CO2 that they would be consuming in the process of recycling and transportation. This data is also used for history matching and for reservoir modeling purposes. And obviously, I showed you a couple of slides on the performance metrics. And then eventually, we hope that when there's a proper marketplace in place for the GHG credit certification, the accounting methods that I have shared with you is a useful technique to bring these projects forward. There are lots of contributors to this particular study, including staff at Battelle, DOE, NETL, Core Energy, and other technical partners that we have. And at Battelle, it can be done. Thank you very much.
Thank you, Sanjay. We have a couple of questions.
Yeah.
So the first one, maybe you answered already, but I'm going to ask you. It is said that all gas is reinjected after low pressure separator. Does it mean that mixture of CO2 plus petroleum gas is reinjected?
No, so the recycle stream that is captured in the high pressure separator first, and then the remaining liquid stream that consists of oil and brine is sent for further separation for any gas that is trapped in that stream. So I would say at this point, about 88% of the gas is captured already in the high pressure separators, while the remaining 12 or 13% of the gas is captured in the low pressure separators and is sent back via the compressor station. So before it goes to the compressor station, there's a booster compressor that operates at about 300 psi. And then that 300 psi gas is sent to the main compressor station, which will compress it to about 12 to 1300 psi. And that'll be commingled along with the pure CO2 that's coming from the Chesterton facility at about 12 to 1300 psi. And that pure, almost pure CO2 gas stream is sent back to the injection facilities. So at this point, if you commingle 99% pure CO2 from Chesterton, and if you take the 96, 97% pure CO2 from the recycled gas, you now have about 97, 98% pure CO2. There may be some hydrocarbon gas, but it is not economical for Core Energy to basically separate the hydrocarbon gas from the CO2. So instead, they send all of the gas back to the reefs.
Okay, thank you. The second question is, are there any monitoring systems in operation, additional, deep, and on the surface?
Yeah, there is a lot of monitoring technologies that we have implemented, including at Chester 16, which is the newest reef in which we have implemented digital distributed accounting as well as distributed temperature monitoring system. Plus, we also have in the monitoring well, I want to say in 6 reefs, we have bottom hole monitoring temperature and pressure gauges that are installed. And in the Chester 16 reefs, we also have real-time gauges that are placed behind casing. So when you're injecting gas in the injection well, in the monitoring well, we have installed real-time gauges at multiple depths that allows us to track the arrival and the pressure and the temperature plume of the CO2 that is migrating towards a production well. So a lot of other technologies, including seismic monitoring and other things that have been implemented. Yeah.
Thank you. And I have a third question. GHG accounting means not only CO2, but also CH4. Do you monitor methane emissions also?
So in our accounting methods, we neglect the amount of hydrocarbon gas because, as I said, by the time you recycle all of the gas, it's almost as if it's pure CO2. So during primary production, any gas that was present was already stripped from the oil. So at this point, the gas stream that comes out of these operations does not have significant component of hydrocarbon gas that could be meaningfully separated and sent back to the market. In fact, Core Energy does not even flare this gas. They will send it all back to the reef.
Okay, I have a last question. Is maybe you touched about it already. Do you have any, how to say, once it goes out of your processing unit, is there any way to divert CO2 from one reef to another, or is it?
Yeah. So we look at, this is a 10 reef complex. So at this point in time, Dover 33 reef and Charlton 6 reef are basically considered to be like late stage reef, in which there is not a significant amount of oil left. But Core Energy will never waste a single molecule of CO2. It'll capture any CO2 that is available from the Chester 10 facility. And if they don't have a place to store it, they will temporarily send it to Dover 33 or to the Charlton 6 reef and then produce it back when they need it for doing new CO2 floods. So right now, for example, it can take any amount of CO2 that it can take. It'll send it to Bagley, or it can send it to Chester 16. So basically, all of this operates in a closed loop system where no CO2 is ever forcibly vented. It's all sent back to the reef. However, recognize that this is a continuous operation. There are no storage tanks of any kind. So if there is any downtime anywhere, there may be cases where they're forced to vent the gas. But typically, any gas that is captured at the Antrim facility is never wasted and is always stored in a reef itself.
Okay, thank you. We are a bit behind, so I have to thank you, and then we will go on to the next speakers, which are Carlos de Dios and Juan Marin from CIUDEN. So you now are able to speak. Just a second, so I can give you the screen. Yes.
Okay.
Okay,
Thank
it's
you,
working.
Thomas. Sorry. Thank you. Can you see the screen?
Yes, yes, yes.
Okay. Thank you very much, Thomas, and welcome to everybody to this third webinar in ENOS project. My name is Carlos de Dios, and I am the Director of CO2 Geological Storage at CIUDEN in Spain, and on my side, Juan Marin, who is the head of on-domain TTP operation. Okay. Sorry, because the presentation is not at the first page. Sorry. Okay. Our presentation is focused on the experiences from on-domain technology development plan operation, which started on 2012. The first part of the presentation will be given by Juan and is focused on how the CO2 is supplied at on-domain and the handling procedure to condition the CO2, because as he will explain, the store condition at surface are cryogenics. And afterwards, I will explain the injection strategy used to inject the CO2 in a deep saline aquifer that is composed of fractured carbonate. So the main fluid transmissivity is dominated by the fractured network, and this is very singular because to date the fluid transmissivity through the matrix porosity is less than 10%. So the floor is for Juan for the first 3 points in the outline: surface facilities, supply and store condition, and on-site CO2 handling.
As probably you know, on-domain site is over an onshore underground reservoir where we carry out our main target, which is the CO2 injection in the deep aquifer saline, okay? Developing strategies to do it, trying to improve it then day by day in terms of efficiency, but don't forgetting the safety for the reservoir and for the area in the surface. Due to that, it was necessary to include several facilities in the Ontomin site directed to let us the CO2 injection and also handling and controlling the product before the injection. In this way, you can see in the down part of on the slide a general view of the pilot, where it's easy to recognize where the two wells are located on the left part of the photo. One of them called HI well is the injection well, and the other in the last part, by the way, is the HA well, okay, the monitoring well. Apart of that, in the middle of the photo, you can see three different tanks. Two of them is included in the CO2 injection facility. And to the right, you can see another installation called water conditioning facility, okay, including 4 different pools to store its water at the end of the photo. In the middle of the area, you can see a building too, okay, where different rooms are located. For example, the main important is the control room, where all the different systems to take to recover data and to operate the different devices is centralized. Yeah, there are a meeting room, different changing rooms, wardrobes, and so on. Okay. As you can see, it's not a very complicated installation, but recover all you need to do a good research, okay, with wide monitoring capacities. Okay. The capabilities of the different parts of the pilot are different, okay, depending of the target of that. Starting with the water conditioning facility, you can see in the upper part the main properties of that. Okay? When we speak about water, I mean always brine. Okay, as you know, when we drill a well and we are where depth as with the depth of the well as much, the salinity of the water we can find is higher. It's implicit with the depth. So in all operations that we need to inject some type of brine, it's necessary that this type of brine will be with the same quantity of salt in some terms, okay, the same salinity of the water from the reservoir, okay, in order not to contaminate that water, yeah, and other problems, other issues. So talking about that facility, as you can see, we have a pump to inject this type of fluid. So it's possible to inject brine with pressures up to 125 bars, with flows up to 10 liters per second. Yeah, always, as I said, using the same artificial brine with a salinity around 25 ppm, 25,000 ppm. So the water conditioning installation is really important in our facility for 2 different reasons. Okay. Firstly, we use brine before to inject CO2 to conditioning the well in pressure terms, in terms of pressures. Yeah. As you know, CO2 is a gas in atmospheric conditions. So the main topic of the pilot is inject that CO2 in liquid state. So we need to condition it in that way. But if when the CO2 get the well, if that construction is not at the same pressure, at least, it's possible to get a root expansion of the gas. So solid state is possible to appear. Okay. So for that reason, the first topic for that water conditioning installation is to condition the well in pressure term, okay, around the same pressure of the CO2 injection pressure at the well. Secondly, that installation plays an important role when the CO2 injection finalizes. Okay, we need to inject brine immediately when the CO2 finishes to clean the tubing. Okay, in order to avoid that gas phase appears when we are going to stop the operation. Yeah. And why not? Mainly the third one reason of that installation is to protect the underground structure on the wellhead from possible blowouts. Okay, it's a blowout preventer, but not common as we are usually to see. It's not a unique machine, a unique device. It's not. It's a complex installation used a fluid. Okay, that is the two reasons that we have this type of installation. Maybe it's the most important of the pilot in security terms. Okay, or safety terms. Other installation, the CO2 injection facility, as you can see in the upper part of the slide, has this type of capabilities. Having a look in the picture, we have 3 different tanks where we can storage CO2, as Carlos said, in cryogenic conditions, that is in liquid state, more or less minus 20 degrees and 20 bar pressure. Okay, so we can storage in the pilot around 150 tons of CO2 in the liquid state. Okay, so that CO2 in liquid state fill 3 different pumps that let us to increase the pressure of that CO2 from 20 bar to around 120 bar. So inside of that installation, we have a gasificator in order to increase the temperature of the CO2 from the cryogenic conditions, minus 20 degrees, to injection conditions, around 40 degrees. Okay, that is the maximum rate. So as you can see in the picture, the CO2 storage in the tanks is supplied by the suppliers to the pilot using by trucks. Okay, using trucks by trucks. The trucks supply the CO2 in cryogenic conditions as well. So as you can see, it's necessary to control that state when we discharge the trucks and when we refill the tanks. Okay. To do that, the common way is the common way in the industrial areas is using 2 different lines, one for liquid state and another for the gas state. Okay, 2 lines are necessary because it's necessary control the pressure of both receipts, tank from the truck and tank on site, discharging gas at the same time when we charge liquid state. Okay, that is possible because per tank has 2 different systems to control the temperature and the pressure of the CO2 storage inside. Okay, one of them control that when the temperature are increasing, one cooling system let the CO2 decrease the temperature, so it's possible to control the cryogenic conditions. Okay? So even in the opposite side. When the tanks are fully, okay, temperature is easy to control, but pressure try to increase it very quickly. So it's necessary one system to reduce that pressure. Yeah, that is the main devices. As I said, installed each time. Per truck have a pump, yeah, to inject CO2 instead of two tanks. So the pumps needs electricity power supply because this supply is external for the trucks. So you need to get to this portion this type of installation. Yeah. So yeah. So that is having a look into the CO2 state diagram, you can see a red mark. Only one idea, the CO2 supply in cryogenic conditions is in that point, as you can see, really near to the line to separate gas phase to the liquid phase. So I have to remark that control the temperature and the pressure during the discharge of the trucks is really important to avoid to change the phase of the gas, and in order to avoid to reduce the pressure of the tanks during the discharge of the truck. Okay, but it's really common if the pump of the truck, for example, is not works properly. The system tries to decrease the pressure. Yeah, so it's possible to lose the cryogenic condition inside of the tank. Yeah, that is maybe the most dangerous part of the operation. Yeah? Talking about the on-site CO2 handling, we have to take attention of the condition of the CO2 when we are going to inject to the reservoir. As you know, it's not possible to inject CO2 at the same conditions that we are storage in the tanks in cryogenic conditions. You are thinking the main property like temperature is in cryogenic condition is minus 20 degrees. It's not possible to inject CO2 with that temperature because in the closed time the most important consequence that the swallow aquifers will be freeze. So that is the main reason. Yeah. So another reason is having a look to the CO2 state diagram is necessary to avoid, as I said, other states that not will be liquid state, gas or supercritical, for example. So to sum up, it's necessary conditioning of the CO2 before the injection, yeah? In two different terms, in pressure and in temperature. Okay, so as you can see in the picture of the left side of the slide, you can see our P&I of the pilot using in the SCADA to control and operation the installation. Yeah? As you can see in the SCADA, the first part of the condition way is to increase the pressure of the system from the cryogenic conditions in 20 bar to the pressure where we are carried out the injection. As I say in the upper part, around 75 bars or higher. Okay, that is the first step in the conditioning way. When the pressure is okay, using the pumps of the diagram, as you can see, we have three different pumps. The maximum pressure we can get with that pump is 120 bar, okay, with a flow of 1 kilo per second. Okay, nowadays our installation let us use two pumps at the same time, so the maximum flow rate is 2 kilos per second, yeah, of CO2. So when the CO2 is at the right pressure, we need to do the other conditioning in terms in temperature terms. Okay, so through the gasificator, so in the imaging, we can increase the temperature from the cryogenic conditions minus 20 degrees to the temperature selected for the injection, depending on the target of the test. Okay, as I say, we usually work from 10 degrees to 40 degrees. We realize it's possible to inject CO2 in temperatures upper to 0. Okay, but the recommendations say that with temperatures upper than 10 degrees is more interesting in order to avoid the hydrate formations. Yeah, that could be the lock, the tubing when we are injecting. Even more when the operation finalizes. Okay. So when the CO2 is connected in pressure and in temperature, it's possible in that moment to inject to the reservoir. Yeah. All the parameters, pressure and temperature, are always in the wellhead part. Okay. So as you know, where the CO2 is going down, pressure goes increased, and temperature goes, depending on the test, go up or maybe controlling the temperature. Okay. So having a look to the CO2 state diagram, I mark it with a red mark, which is the range of the state of the CO2 where we usually work injecting CO2 to the underground structures. Okay. So as you can see, it's possible even to inject in the supercritical phase, avoiding always the gas phase as much as possible. Yeah. But as you can see, when the CO2 going down, controlling that is not easy because it's out of our hands. Okay. Only depends on the temperature of the reservoir and how is the speed of the flow and something like this that supercritical phase appears much or less. Yeah. So that facility, yeah, as you can see, let's adopt this type of conditioning. Both of that is really important previously to open the final valve that we let us inject CO2 to the well. Yeah. As I can see, before of that, it's necessary to condition the well using brine at the same pressure. Yeah, as I said, 75 bars or more. Okay, that part is very important. And when we CO2 injection finalized, we need to inject brine at the same pressure again, and in that case, in order to clean the tube, okay, around all the length to the reservoir, okay, pushing the CO2 inside.
Okay, in this slide you can see the first seal reservoir of Antomin site on the left side, the geological column, and being the reservoirs of Peña Formation, as Puneet mentioned before, of fractured carbonates, the upper part limestones and the lower part dolomites. And the main seal is the Mawalkar. The secondary seals are the Dagger, Purbeck, and well. Two wells were specifically drilled for the project, with a distance at the surface of 80 meters and at the depth close to 180. The injection well, you can see in this part of the slide, is equipped with different monitoring devices. 2 PT sensor at the bottom hole, a DTS and DIS, distributed temperature and acoustic sensing systems, to control the CO2 injection, the ERT electrodes to perform electrical tomography between the wells. It's a cross-hole tomography. And the observation well, you can see here, is different parts of the seal and as well as the Peña Formation, the reservoir, with inflatable packers allocating different areas of the reservoir and the seal to analyze how is the fluid transmissivity in the parts. Regarding one explanation, this is the end of the CO2 injection facility, just over here, and the brine conditioning facility. 2 pipes to inject CO2 and to inject brine. As he explained it, and we will see later, this is the singular CO2 injection strategy we use at Puneet. This is the wellhead pressure at the Christmas tree, and on the right side you can see the deep fluid sample is at U2 to extract reservoir water samples in reservoir condition. That means that the samples are in under temperature and pressure of the reservoir. That means close to 140 bars and 45 degrees centigrade. Okay, this is the liquid CO2 injection workflow. As Juan explained, 3 stages we use in this workflow. With alternative injection of brine and CO2. You can see on the left side of this graph the brine flow for well pressurization. It means we have to reach the value of 75, 80 bar. This is a set point. It's a critical and crucial set point established to inject the CO2 in dense phase. That means in liquid phase or supercritical phase, very close to the liquid phase, as explained in the thermodynamic diagram of CO2. Afterwards, the second stage of this workflow is the CO2 conditioning previously to be injected. This explanation given by Juan is we need to pressurize the CO2 and as well to increase the temperature because the cryogenic conditions, minus 20 degrees centigrade and 20 bars, must be increased to the range between 10 and 40 degrees centigrade and upper the 75 bar as set point. The third stage is the CO2 injection. Here, green line. The flow, in this case, 2 kilograms per second. As mentioned by Juan, we are injecting the CO2 using 2 pumps at the same time. That means we are coupling 2 pumps for CO2 injection. And finally, again, the brine flow to clean up the tubing and as well to build a seal. Is sealed with the brine in the injection tubing for avoiding CO2 leakage. This liquid CO2 injection procedure was developed according to the conditions established in the project OxyCA B300. That was the project under its framework. We designed it and constructed the pilot. And in this project, the conditions were to transfer the CO2 from pipeline to the trapping condition in the deep saline aquifer. So this is a patented process with this number, that's Spanish patent. And just important to note, if you have a look just over here, that is the buttonhole pressure, taking into account this recorded values belong to the buttonhole to the depth of 1,400 meters. That means that the overpressure at the buttonhole is just 20 bars, but the wellhead pressure, as you can see here, is close to 80 bars. The reason that the wellhead pressure is not transferred at all to the buttonhole is due to we have installed a tubing choke. That means a drop pressure valve at a depth of 1,000 meters to avoid high overpressure at the buttonhole. And this high overpressure could fracture the reservoir and the seal, putting at risk the per-seal reservoir. You can see here, in this graph, the CO2 injection test conducted in ENOS project during 24 hours In this case, establishing a set point of 80 bars. This is the control mode used in this test. That means that we maintain during the test always the same value of the pressure, 80. So at the top, you can see the buttonhole pressure evolution during the injection and during the follow-up period. In green color and purple, how is the bottom temperature evolution during the injection CO2? And in this case, and in this other, this important decrease due to the brine injection previously to pressurize the wall until to get the value of 75, 80 bars, and afterwards for the tubing cleaning. Here you can see as well the wellhead pressure, the wellhead temperature, and from this part of the graph to the right, the follow-up. Important to note that during the follow-up in this type of reservoir, where the fluid transmissivity is dominated by the fractures, as mentioned before, the pressure time recovery is usually longer than in that media that the fluid transmissivity is dominated by the matrix porosity. Regarding the thermal profile, previously the injection in green line and after the injection in blue line, you can see here that the CO2 injection during 24 hours in liquid conditions produce the cooling along the tubing. You can see more. This green line is more or less the geothermal gradient along the wall, and this is the temperature of the CO2 in the different parts of the well. Here, at 1,000 meters depth, where the pressure drop valve is installed, the preheating occurred due to the diameter of the tubing is reduced to the choke, to the drop pressure valve, and afterwards, due to the CO2 is gas, at the exit, the Joule-Thomson effect occurs. You have a look to this thermal profile from the surface, 10 degrees centigrade, and at the bottom hole is more or less 31, 32 degrees centigrade, and taking into account that the pressure at this part is, you remember from last slide, is 160 bars, the injection was performed in liquid phase. Probably in this part of the tubing could be in supercritical phase, as Juan explained it in the graph. On the right side, you have the bottom hole temperature history. As you can see, the injection of CO2 in several tests produced a relevant decrease of the temperature from 45 degrees, that is, let's say, the baseline, previously to the injection, to, in some case, 25 and 27. That means that a matter to study is how this temperature decrease and the temperature evolution during the injection could impact on the geomechanics of the reservoir and the cell. The injection was performed in liquid phase, and the trapped CO2 is in supercritical phase. So that is all from our side. We are open to questions if there is one. Thank you very much.
Thank you. So we have one question. I have some echo in my, so maybe, okay. I will mute you the time I ask the question. So the first question is regarding the numbers on-site CO2 handling slide. What is the CO2 pressure and temperature at injection wellhead, and what is the estimated or at the bottom hole? So I think you kind of answered that on your last slide. I give you the.
You can see here. Sorry, here. Okay. As Juan explained during the presentation, we try to be as most effective as possible to show the liquid CO2 injected on site is probably the most effective operation. So to do that, it's needed that the wellhead pressure is always equal or higher of 75 bars. This is the set point. And this operation was conducted in pressure control mode. That means that the CO2 injection pumps are working to maintain this value from 75 to 80. You can see here more or less how is the transient period during the permanent period. Okay, so 80 bars at the wellhead. But at the bottom, you can see that we have reached 160 when the baseline is 140. That means that we have increased 20 bars, the overpressure at the bottom. And this is due to a drop pressure valve was installed in the tube. So the final pressure is 160 and the final temperature is more or less, you can see here, is 35 degrees centigrade. That means that the conditions to store CO2 at the reservoir is in supercritical phase, but the injection along the tubing is in liquid phase.
Okay, I have a second question from Sanjay, who asks that if you have a DTS optical fiber installed in the injection well. DTS is distributed temperature sensing for those who don't understand.
This is a DTS. This is a DTS graph, and plotted directly by the system. Okay, and you can see here at the injection well. Okay, I cannot see because it's the screen of the webinar. But however, you can see at the injection well 2 lines on the right side. One for the DTS, distributed temperature sensing system, and other for DAS, distributed acoustic sensing system. On the other side, on the left, is the U2, the deep sampler.
Okay, thank you. So I think it's quite a long webinar, so I'm gonna still ask if there's one or a few questions, maybe for the whole panel of presenters. In the meantime, I have to thank you all again for presenting to this webinar and of course for attending. So I don't see any hand raised or any new questions. Well, anyway, so thank you. I remind everyone that you can find all the information on these webinars on the ENOS website, which is ENOS, I don't know, enosproject.eu, I think it's the website. If you have any comments or if you want to be added to the newsletter, you can send me an email that I showed on my presentation. It's t.legueno@brgm.fr. And if all the presenters agree, we have a recording of the webinar that we can put on the website, but I will ask your agreement, your written agreement at the end. And I think with this we can close this session. I think it's been we had a great diversity of presentation from the whole chain, which was really interesting to have this very broad view of CO2 from the source to the sink, basically. And I don't know if any of you want to add something. Okay, I don't. I think it's been a long webinar, so I think I'm just going to thank you again. Thank you, everyone. Thank you, ODS, for the webinar, and we'll keep in touch for the next webinar that will be announced pretty soon, I guess. Thank you, and goodbye.
Bye-bye.